Okay, hello everyone. Today our topic is about magnetic effect of a current. Okay, so let's move into the first slide, and here you can find there is about magnetic field around a wire. Okay, so maybe 100 years ago, that a scientist and he's a professor, and one day he just go to the lecture and wants to take a go to the hall, wants to take a lecture for his student. Okay, and he just doing an experiment just to show there's a circuit and there's a current in the circuit. Okay. And at that time, the European is very famous for like traveling. Okay. Like traveling by boat. Okay. So they're very fascinating using a compass to find their way. Okay. So once he opened or like close the switch, close the switch or make the total circuit has a current inside of this. And he find that there is a phenomenon that the compass will maybe have a little bit deflect. Oh, so maybe here that represented for, oh, maybe here a current can afford a magnetic field. Okay, so the scientists make few years to design and to define whether there is a deflection for the compass. Okay, so you finally realize that, oh, maybe a current can afford a magnetic field. Or you can also say there is a magnetic field around a wire with current, okay? So here you can find that in this figure, it shows the magnetic field. You can find there's a like ripples, there's a circle around with another circle, okay? So here are some features about the circle. The first feature is that the magnetic field lines are circles, that the circles have the same central, okay? This is the first feature. And secondly, you can find that the health is strongest close to the wire. Because last class we have said before that if you have a very high density of the magnetic field lines, that means you have a strongest magnetic field, right? So here we can find, oh, maybe here, closer to the current has a stronger magnetic field, okay? And the third is that increasing the current maybe also increase the strength of the field, okay? So there are the three properties for the field, okay? So let's move to the next part and how to like draw the or like the magnetic field. And you can just raise up your right hand and just like grip the rod, okay, like this way. Just grip the rod, and you'll find that maybe your thumb is just putting upward, right? And you'll find your four other fingers are just rotated around the rod, right? Like this way. Okay. So here, your thumb represents for the direction of the current, and your four other fingers represent for here it is the direction of the magnetic field. Okay, so maybe from the bird view you can find that, oh, maybe the like the magnetic field is just rotate in a anti-clockwise direction, right? So this is how to find the magnetic field by this way. Okay, so we can call this rule as a right hand grip rule. Just try to grip like a rod and before you, okay, like this way. Okay, so your thumb means the current, and your four other fingers represent for the direction of the magnetic field. Okay, so like here we just discussed about how to determine one single straight rod, and here we just maybe rotate the rod and just to make it as a curve and then make it to become a circle like this. You just maybe change its shape like this way. Okay. So we can also find if there's a current in a circle wire, and here you can find there's also afford a magnetic field, okay? So the magnetic field is just very similar to a magnet like this way, and it has N, North Pole and South Pole, okay? And here you can also using your right hand, just trying to grip on the, like the, maybe for the wire, okay? And your four fingers represent for the like current direction, and your thumb means the north pole direction. Okay, so you can find maybe on the left figure you can find like this is a current direction, and you're using your four fingers just to grip the curve, and maybe your thumb represents for the north pole like this way. Okay, this is for the figure. Okay, and the figure on the right you can just try to use your hand and trying to grip the like the curve, and you can find that, oh, maybe here is the rod, sorry, there is the current direction, and you can use your right hand to grip on it, okay? And you'll find that because this is just combine many turns of the wire, so the magnetic field of this is very strong like this way, okay? This is for the magnetic field of this, and your thumb just represent for on the left. So on the left is the north pole, and on the south is the south pole. You can use the magnetic field distribution to draw the graph, okay? Here it is. And you can also call this is a right-hand grip rule, and this is just change the direction. Like before, we were using the four other finger to represent for the magnetic field direction on a straight wire, and here we just trying to reverse, and you are using four fingers to represent for the current direction and the thumb represent for the magnetic field. Okay, so here it is, and just trying to solve the exercise 3, please. Okay, here's a very interesting example like this. Okay, just trying to solve the problem. Okay. Okay, so right here in this figure, you can find there's 2 points, x and y, okay? X and y, okay? So for x and y, we can say, oh, maybe here we can say, oh, maybe you can just trying to using your right hand, right? Because it's a solenoid, right? And you can just trying to use your four fingers to represent for the current direction, right? And here you can find there is a current direction, okay? Just from the upward to downward, okay? You can use your hand to grip it, okay? And maybe here your thumb that represent for the north pole. So here is for the north and here's for the south. Just consider it as a very big magnet, right? Like this one. And we have said it before, for the magnets, we have the magnetic field like this way, right? The north is just to release the magnetic field, and the south is to receive the magnetic field, right? So you can find at x and y, they're very tense, right? Because they have very closer distance. That means they're very high density and very big magnetic field. And on that, you can find the lines are just separate, right? So you can find the distance between each other is very big. That means the wire is very sparse at Z point, right? So we can say, oh, here for magnetic strengths at y and x, they're equals to each other because they have the same density of the magnetic lines, right? And at z is very small because the magnetic field lines are very sparse. Okay, so this is for this way. So we can say, oh, for x and y, they're the same magnetic field, but for z is smaller than in x and y. Okay, so we can say, oh, here magnetic field strength at y is same or equal to x, and they're quite less than the z. Okay, so finally we choose the A as our final answer. Okay, so this is for today's lesson. So see you next time. Bye.